Okay, welcome everyone. I'm actually going to do this in English as an exercise because I'm going to have this presentation in Bristol next month. Code as a crime scene. It's about how we interact with our code. And I'm going to talk a lot about interaction patterns. And when I talk about interaction patterns, I mean what kind of code are we modifying, how frequently do we do those modifications, and what's the nature of the web of code we're modifying. The idea is that there's a lot of valuable information in those patterns. And by mining and analyzing that information, we can learn a lot about the software. We can get early warnings on the potential design issues, and we can also get ideas for future refactorings and evolvements. And I also see some familiar faces, so those of you who know me, you know that I have a parallel career within psychology. So I'm quite interested in things like team dynamics and group processes. And I think that software, it's a social game. And with those techniques I'm going to show you today, can actually get some feedback on how well that game works for us, right? And we're going to have a discussion afterwards. The presentation will be approximately 40 minutes, and I'm happy to take questions as I go along. Right. So, complexity. I think that's the most challenging aspect of every large-scale project, to control the complexity. And my first bullet point here about maintenance. Maintenance is interesting because it's often viewed as a problem. I would say that it's not. Maintenance is actually a good thing. Why? Does anyone have an idea? Why do I like maintenance? Yes, please.
It keeps the program alive.
Yes, of course. Maintenance is a good thing because it means that we have users. Not only that, we have users that care enough about our programs to request changes to them. So maintenance is a good thing. But it's quite expensive. How much do you think we spend on maintenance? Given the total cost for a product over its complete life cycle, how many percentages are maintenance? 90? That's a good digit, because Fred Brooks said 90% in the 70s in Mythical Man Maps. But subsequent research has shown that maintenance is typically somewhere between 40 and 80%. And the average, of course, 60. So we spend 60% of our money on maintenance. What do we get for those money? Well, it turns out that of all those money, 60% are spent on modifications to existing programs. So we're not adding new features, we're modifying existing programs. And to me, the lesson is that if we want to optimize some aspect of software development, we should optimize for maintenance, because that's where the money are, right? So we should optimize our programs to make them as easy as possible to modify and evolve. This 60-60 rule, by the way, is coined by a man named Robert Glass. And I recommend you that you check out his writings. I have a few references to him. So, we need to design for maintenance. And if we run into any issues, our typical way to address it is with refactorings. Now, what I'm going to talk about today is not those small refactorings where you rename a variable or introduce a new method. I'm going to talk about large-scale refactorings, things that change the very fundamentals of the design. And those kind of refactorings are impossible to automate. They are also high risk, and they are expensive. So we want to make sure when we do those kind of refactorings that we are refactoring the right thing, that we actually get some return on our investment, right? And I hope to show you techniques today that can guide us. Another thing I'm going to talk about is parallel development. Parallel development is a huge challenge in any large-scale project, and particularly software, I would say. Let me ask you, how many of you have read The Mythical Man Month by Fred Brooks? Does anyone know Brooks' law?
If you add developers to a late project, it gets stable.
Yes, exactly. It's I think he phrases it something like adding more manpower to a late project makes it even later, right? And we're going to talk more about parallel development later. The reason that it's more expensive to add people to it is because of the communication overhead. And you really want to avoid it because parallel development, as we will see, has is strongly correlated with the defect rate. And I hope to be able to show you techniques that will help us to detect those kind of problems. Another challenge in our large-scale project is that we don't always know what we do, right? And a few years ago, I was in a project where we were approaching a deadline, and we were fixing a lot of bugs. And one morning, I was really productive. I fixed 5 bugs. I corrected 5 bugs. In the afternoon, I had 6 new bugs. It's really interesting, and it really wears people down. After a while, you start to ask yourself, when will this end? When are we really done? And I think it would be great if we had some way to monitor that and actually give us some feedback on our work. The final thing I'm going to mention something about today is automated tests. And I think we all know the benefits of automated software tests. But I also think the problem is that in practice, it's terribly hard to get right. And I've seen it several times that you start to automate something, you get some leverage, and after a while, the test somehow takes longer and longer to maintain. They're harder and harder to evolve. And the automated tests become a time sink. You actually spend more time maintaining your test cases than you are developing your software. Now, that were a few problems. How do we typically address them? This is one way. There has been a lot of research on software metrics since the 70s. And those metrics are intended to measure complexity in our software systems. And the first one is called McCabe cyclomatic complexity. Does anyone know McCabe cyclomatic complexity? I know that you know it. The idea, anyway, is that you consider your program as a graph, and then you count the number of possible paths through it. And each path adds a complexity value. And the higher that value, the more complex your software. And yeah, I think I've been using that a lot, that measurement, and it makes sense, because every possible path puts a load on our cognitive working memory. And it's a strictly limited resource, so there's just so much that we can hold in our head. This is another quite common measurement. It's called coupling. And afferent coupling, that means how many different components do I depend on? This very component. And it's basically the risk that I will change. The more dependencies I have, the bigger the risk I will change. And the other type of coupling, afferent coupling, that's the cost for changing me. That's how many different components that depend upon me, right? So I think that also makes sense. So what's the problem with metrics?
What do we compare them with?
Exactly. What do we compare them with? And there's one project. It's called iPlasma. Have you heard about it? They actually develop some industry standards for those different metrics. And then they run your program and they say, okay, you have a C++ program and the typical symptomatic complexity for a method is 7.1. Yeah, that's one approach. But it's hard. It's really hard to choose the right metric. And besides, the major problem I have with them is that they don't work. This is one interesting quote. And this quote is from 2 researchers that actually tested those different kind of metrics. And they found out that as soon as you start to control for the number of lines of code, those metrics don't add any further prediction. The number of codes is a number of lines of code it's a really primitive measurement, right? And these are not doing better. Then I have my favorite quote. The use of metrics to manage software projects has not even reached a state of infancy. This is the same guy, Robert Glass, that wrote about the 60-60 rule. And Glass means that the more complex our problem is, and software is a complex problem, the faster our different strategies break down. And the first strategy to break down is quantitative methods, like software metrics. So what should we do instead? Robert Glass means that we should use our intuition. And, you know, as a psychologist, intuition is, I love it, it's really beautiful, right? But what is it really? Intuition is basically, it's an unconscious process. We all have a certain expertise within software. We have a lot of experience developing software. And intuition is nothing else than something in the situation, perhaps something we see on screen in our code editor, that triggers a lot of that accumulated expertise. So intuition is just recognition. Now, intuition is a good thing. The problem with it is that it's quite sensitive, as all other unconscious processes, to a lot of cognitive and social biases. I won't go into those biases now in this presentation, but I'd love to talk about them later. But there's another problem with intuition, and that is that it doesn't really scale. There's no way that any one of us here, no matter how good we are, can scale our intuition to encompass a system of 1 million lines of code. There's no way to do that. So I would say what we really need are some techniques that help us to narrow down the search area, to focus our attention and focus our expertise on those parts of the code that really matter. And my idea is to look at a completely different discipline that have exactly the same problem, and that field is forensic psychology. Does anyone know something about profiling of criminals? Do we have a profiling expert here? Yeah, that's good. Many people have probably seen Silence of the Lambs with Hannibal Lecter, right? He's doing a profiling. Now, he thinks into the mind of the offender and he somehow manages to get their personality portrait, I think. The problem with that technique is it's really good. The problem with it, it's so limited in scope, it only works in Hollywood. But the good thing is, there are some more scientific methods. So please allow me to give you a 2-minute introduction to geographical profiling of criminals. And perhaps we will be able to tie it back to software. Now, as I started to study criminal psychology, the first thing that struck me, because it's obvious, is that criminals, most of the time, they behave just like the rest of us. They go to work, they go to the movies, they go to restaurants, they go shopping, perhaps they even pick up the kids from school. So they move around in a certain area, and for a crime to occur, there has to be an overlap in time and space between an offender and the victim. And it's during these movements throughout an area that the criminal finds the opportunity for a crime. And that tells us that the crime scenes are never random. The crime scenes contain information, geographical information about the criminal. And what I'm showing you here is a map of 19th century London with the crime scenes of Jack the Ripper. Do we have a Jack the Ripper expert here? Come on. A little bit? Yeah? I'm going to come back to you with a few questions later. Jack the Ripper. The interesting thing is, what I got here is a geographic profile of Jack the Ripper. And what you do is that you basically take each crime scene and consider it as a center of gravity. And then you weight the different centers together. And there's another aspect too, because psychologically all distances are not equal to us humans. So crime scenes that are closer to each other gets a bit more weight. And that narrows our search area down to this red hotspot here. And that hotspot, that's where we're going to focus our efforts. That's the area to supervise and search if we want to find a Ripper, like in the 19th century. And it's, according to some studies, this method has a 70% chance that the offender has its home base within this hotspot. Right? So, as I saw that, I thought, wow, wouldn't it be great if we had something similar for software? Something that allowed us to take those million lines of code and narrow it down to a few hotspots that we have to search. But before we continue, perhaps you want to know if this really works. After all, Jack the Ripper was never caught. And do you know who he was?
Do I know who he was?
Yes, Jack the Ripper. Do you have any prime suspect?
No, not really.
I don't know that much about Jack the Ripper, but I know that 20 years ago, an interesting document was found. It was a diary written by James Maybrick. James Maybrick was a cotton merchant from Liverpool, and he claimed in that diary to be Jack the Ripper. And I mean, there has been literally thousands of Jack the Ripper fanatics that have tried to show that that diary is a forged, that it's not authentic. And it's been 20 years, and nobody has succeeded to falsify that diary. So for all that we know, James Maybrick may have been Jack the Ripper. And the interesting thing is that when he went to London to do business, he rented a room in the Middlesex Street. And look where it is, right in the middle of the hotspot. Okay, let's move away from Jack the Ripper and talk about something more pleasant, software. What if we want to apply this to our systems? Do we have a geography for our systems? Has any one of you seen Code City before? There are lots of possible visualization tools for software, but this one is my favorite. What it does, this is a Java system, by the way. So it takes the Java code, and each package becomes a city block, and each class becomes a building. And the height of the building is based on the number of methods in the class. And the base is based on the number of attributes the class has. So the larger the building, the more complex it is. And if we were using traditional metrics, we would immediately go for those big towers. Those would be our complexity spots. But I would say that those are not necessarily the most interesting ones, because complexity is only a problem if we have to deal with it. If it turns out that that code has been stable for 2 years, we are not doing any modifications there, perhaps we could spend our efforts better somewhere else. And I think just like we can get information from crime scenes, we can get a lot of information from our version control systems. course, they actually record a movement throughout that area. Every commit that we make carries a lot of information about what we are doing with our projects. So this is another way to look at it. This is a concept called heat maps. There are a few tools that generate heat maps. But what they do is that they take all commits that are done in a system, takes them from the version control data, and visualize them. And the brighter the color, the more activity. So this is one file that has been changed a lot. And there is a smaller file that has also been changed a lot. Now, this is really interesting because it tells us what areas of the code are we working on. But I would say that it's still not complete. Why is that? It's because it doesn't tell us anything about the nature of that code. Perhaps that code with a lot of activity, perhaps it's beautifully written, perfectly structured, and made for parallel developers. Perhaps there's no conflict there. Or perhaps it's a complete mess, but we cannot tell from this picture. So what I would suggest is that we merge our two words, get something like this. And we immediately see that, oh, this is the area where we spend our development effort. And the colors here could be based on different things. They could be the number of changes, but I think a more interesting number is the number of developers that are working in parallel. And that's information that's possible to extract from version control systems. I have to tell you too that as far as I know, there's no system available today that does this kind of visualization, that combine those two words. But I've been doing it a lot, but mainly I would use Python to write a few scripts and gather the data and mine it and analyze it. But the step to actually visualizing it is not that far away. And there's another interesting thing that we can find out by mining our version control data. We could find out about implicit dependencies. And that's a concept called logical coupling. Has anyone heard about logical coupling? Yeah.
No, vaguely maybe. I guess you mean when two files are always modified at the same time by the same.
Yes, exactly. Exactly. So it's different from it's different from the typical way we reason about dependency. A typical physical dependency is that one module depends upon another. They are coupled together, and when I change that one, I have to change that one too. Here we don't necessarily have a coupling between them, but yet they keep changing in the same commit every time. Why is that? Does anyone have an idea? What kind of modules do that?
Could be two sides of an API, maybe.
Yes, of course.
Could also be tests
Yes, the production code and the test code.
or unit tests.
Yeah, or unit tests. But normally it would have a physical dependency between the unit test and the production code. But yes, they are certainly coupled and tend to change together. It could also be, I have seen this a lot with high-level, system-level automated tests that are black box tests. Yet they keep changing, and that's something we can expect. But in case we don't expect it, we could actually learn a lot by investigating the reason for that coupling. And I'm going to show you an example of that soon. Another great advantage with using version control data, I think perhaps one of the greatest advantages, is that it's language neutral. That means I can compare data that's written in different languages. For example, I could have my whole application written in C#, and I could use something like Ruby or Python to test it on system level, and still be able to find logical coupling between those two words. And I think that's really valuable. Now, before I show you the actual applications of this, I want to talk a little bit about parallel work, because many of those techniques boil down to avoiding parallel work. We already talked about Brooks' law, adding more manpower to a lake project. There are several studies that found out that the amount of parallel work on a component predicts the post-release effects in that component. But I think it's even worse, because besides the defects and the communication overheads, you have another problem with parallel work. And the reason is that when I start on a new project, I go into a module, I check out the code, I read a little bit, and then I make a modification. And a week later I come back, I go into the same code, I read a bit more, and I make a modification, and over time my understanding of that module grows. I learn more and more. Now, the problem is, if every time I go into that module, if every time the code looks completely different, I lose that learning opportunity. And I think that's a terrible waste of cognitive cycles. So parallel work is something that we want to avoid. And in case we have a problem, we don't always know if it's a problem or if it works out. So we may have a feeling, but we're actually able to measure that. And in this final part of the presentation, I'm going to show you a few examples, a few case studies of how it could look. The first one is about logical coupling. And this one is a case study from the Firefox, done on the Firefox project. And this is just a really small part of the source code. No, what the researchers did was they mined version control data from Firefox, and then they looked for correlations. They looked for packages that didn't have any physical dependency upon each other, but that tended to change together in at least 80% of the commits. 80% is quite a large number, right? And what they found out, that most of the time, they saw this pattern. The packages under the root directory with the same name, they tended to change together. And if you look at Firefox, that seems like a deliberate design choice. It simply means there are different ways to slice an architecture, and that's one possibility. And it's easy to remember. If I change the places here, I have to change in two different places too. So that's not that interesting. The interesting things are those correlations that don't match that architectural principle, that break it. Those are the ones that are a problem, that we should investigate further. And one of them is this one. They found out that in more than 80% of the cases, content and themes tended to change together. And if you find that kind of logical coupling, your next step is to drill down on file level and check exactly which files are changing together. And if you want, it's version control data, so you can drill down to individual lines of code and really identify the coupling on a really low level. And once you've done that, you will get a pretty good idea about what you should refactor and in what direction. Because there are probably some small module here looking to get out. I talked a bit about automated tests. I think it's interesting to measure the rate of change, the change frequency between your production code on one hand and the test code. And the interesting thing is the general trend. For example, if you find that your production code changes a lot with virtually no changes to your test code, what do you think that means?
Tests.
Yeah, exactly. You're probably not doing any tests. That's easy to spot, but the other way around, that perhaps your test code is changing more often than your production code. I've seen that in a few projects, and if you see that trend, if you spot that pattern, you probably, there may be good reasons for it, but most of the time it means that you have a real quality problem with your tests. There may be different reasons for it, but I would definitely go and investigate that. And I'm talking about system level tests right now. I've never done this on unit tests, but I think it would be an interesting exercise too. But if you find that pattern, I would suggest the same thing as I do it with the hidden modularity, to drill down on individual files and find out exactly what things are changing together. And you often notice that in the daily work, because you make a change to the production code, you change one class, and suddenly 10 test cases break. And you have to go into all those 10 test cases and modify them. Perhaps they are having too many responsibilities, or you really have a quality problem with implementation there. Now, here's another application. What we see here is, this one is about code churn. Has anyone heard about code churn before? This is a really valuable feedback on how we are working as a team. And code churn is the change rate of our source code. The more lines of code we change, the higher our churn rate. And this is a log from one of my projects. It's from Git, and with some options, Git is able to show us the churn. For example, here, I've changed one file, I modified 5 lines, 3 insertions, and 2 deletions. Right? And here's a much, much bigger commit with many more changes. And we're, of course, able to mine that data and analyze it. And again, the interesting thing here is the general trend of the data. So let's see what we can learn from the different patterns. The first one here, you see you have a certain number of lines of code, and then you have a churn level that's fairly stable, and it's actually decreasing when we're approaching a release. And this pattern is something that you could expect if you're doing something like continuous delivery or continuous integration. And I would be quite happy to have that kind of pattern. But here's another one that I've seen at least once, and I know several other organizations that have exactly that pattern. Now, look at our code churn here. Nothing happens, and we get a spike. Again, nothing happens, a new spike. Nothing happens, a new spike. Why is that?
Hermit developers.
Sorry?
Hermit developers.
Yeah.
They go to the cave, hackathon, 2 weeks later you get a huge...
Yeah. That's probably one of the reasons. But why? What happens if you investigate this is that there's typically 2 or 3 weeks between all those spikes. Why exactly 2 weeks? It's not possible that every feature takes exactly 2 weeks. Why is that? Because we typically have a small deadline here. Perhaps we are doing sprints, iterative development, and that's the day before our demo. So everyone wants to deliver. And I think that deadline brings out the worst in people. So the code was probably rushed to completion. Besides, 2 weeks of work is way too much to integrate at once. And third, because you have a lot of parallel development on different branches, and then it all comes together within 1 day, it probably means that those features were never tested together, and we don't know how they will interact. So this is definitely a problem if we spot that. The third one is what I talked about earlier today. You get closer and closer to a release, and yet your code churn just increases. For every bug you fix, you introduce to a new. You don't really know where you are. And this is a big problem because code churn is quite a researched subject. And it turns out that the pre-release churn rate is highly predictable of post-release effects. So those modules that have a high churn rate are the most likely to contain the most effects post-release. And this data is quite easy to get. There are even tools that generate it automatically. If you use Subversion, you could use something like stat.svn, and they will print the pattern for you. Now, I'm almost done. Just want to show you one last thing. I think that the commit messages themselves, the messages we write as we check in the code, carries information too. And that information could be, I think, could be useful to stimulate discussions and get a different perspective on what we're doing on an everyday basis. Now, this word cloud is generated. I took all the commit messages from an application I've been working on and threw it into the cloud. And that application was a research project to study false memories in psychology. And as I saw it, I was actually quite happy because, at least at first, because DRM is a technique to introduce false memory to people. So that's a good thing. It's something from the domain that I spent a lot of time on. NBAC is a technique to measure working memory. So it's also part of domain, that's fine. But apparently, I spent a lot of time on improved, spelling, corrected, error handling, and I didn't really expect that. It gets quite dominant here. So even if I wrote the application myself, I actually learned something about my ways of working. And I learned that to scale an application on multiple servers is hard. Now, finally, just want to mention where I think all this is going. We talked a lot today about modifying code and what we can expect from our modification patterns, but I think it's just as much information in our read patterns. And wouldn't it be great if we could have a system that every time I check out some code, I get a recommendation, you know, like Amazon are doing with their book recommendations, that we get this recommendation that developers that read that code also read that module. I think that would be really useful, and there are actually systems, research projects that are working in that direction. Finally, Google have a system to warn developers as they check out buggy code. What they are doing is that they base their assumption that code that has been buggy in the past is likely to contain bugs in the future too. So every time you check out code that a lot of bugs clustered, you get a warning. And what happens with that code? After a while, it gets refactored. The quality problems disappear. So they have a time dimension in their metric that hotspot with all those bugs cools down over time. And I think we could use the same thing for parallel development. You have been imagine checking out some code and getting a warning. Hey, please watch out. There has been several other developers in this code over the last week. I think that could be really useful feedback. And I also think that there will be commercial applications around finding version control data and combining it with additional metrics. So that's everything I wanted to say in my presentation. My take-home message is have a look at the version control data. It's really useful. It's a goldmine, and it gives us a lot of valuable information and feedback on what we are doing. Thank you very much.